penultimate talk is the William Smith medalist Francis Wall, who is going to talk about responsible manufacturing. Geologists help get it right from the start. Over to you, Francis.
Thank you very much. Right. So I put the title here for this afternoon, Responsible Manufacturing. And normally I might have put responsible mining or something like that, but in the first few slides I want to pick up on a theme of Marianne's, that feldspars know where they are in a dike. And I'm going to point out to us geologists where we are in the world, and then think about what we are going to do about it, perhaps might be a theme. All right. So, responsible manufacturing then. Everybody has probably got one of these in their pocket, hopefully switched off somewhere or the other. And whenever we start talking to the public about minerals or ores and things, how many times do you do something to do with a smartphone? Because everybody knows about that and everybody is connected with it. And how many people ever think about where the start of that smartphone is and where this stuff has been taken out of the ground? Because, of course, it has. All of those materials that we use throughout the whole of manufacturing have come out of the ground at the beginning of their life in some way or other. And it's not just about smartphones. Right now, we've had the recent Committee on Climate Change report. It's all about manufacturing electric vehicles and the specialist metals that go into that. So I'll start a talk and talk about 4 times more copper in one of these things than a normal car. There's kilograms of rare earths in the direct drive motor. There's lithium, of course, in the batteries that we haven't been using before, and things like cobalt that hit the headlines. So we are connected with these technologies, and it's all about manufacturing these offshore wind turbines that are going to produce the renewable electricity to power the electric vehicles in the UK by 2035, is it? And, of course, solar panels as well. And all of these technologies have 2 points about them. The first is that if we want a low-carbon world, if we want to decarbonise our industry, then we're going to need to mine more raw materials out of the ground under land or sea than we've ever done before in the history of humankind. And the second one is that those kinds of raw materials are a much more diverse bunch, including odd bods like rare earths and things, than they were early in manufacturing history. So more stuff and more different kinds of stuff. And that leads to things like the critical metals agenda and the things that have really reinvigorated economic geology in the UK and throughout Europe and places like North America. And so this is big news for us. And here, I know I'm preaching already to the converted. And from this slide, I'd like to go to this slide. From the converted Ellen MacArthur Foundation, who I think are one of the most knowledgeable and quite mature organisations that thinks about the circular economy. And here is the circular economy and the manufacturing circle and what they say we should be doing here in blue up there. And can you find us on there, anybody? Where are we? After that big introduction, we've got to mine more than we've ever done before to service the low-carbon economy. I'm going to have to use my pointer. And maybe you found us up here. A little mine truck. I think there's supposed to be some kind of oil rig there next door to it for the oily people. And we don't even there's no minerals or anything on there. We're called finite materials. And we're blocked by a barrier of please substitute, virtualize, restore before you go into the manufacturing supply chain, and then of course it's round and round, and that's huge, and we're extremely small. And I think this is why I didn't put responsible mining, I put responsible manufacturing, because I think we have to get together with our colleagues in manufacturing industry and perhaps re-educate them about the fact that they need stuff, and they're going to need us to help provide stuff in the way that we need to provide it now. And that's what the rest of this talk is about then, the way that we need to provide it. You're probably all familiar with things like this, Fair Trade Mark, the Forestry Stewardship Council, Fish, Soil Association. What about our raw materials? Any obvious mark from that? In fact, there are quite a few schemes that I could put up. None of really, I would say at the moment, are familiar at all to us on the end of the supply chain as consumers, but the industry is almost falling over itself at the moment to be seen to be doing the right thing, whether it's the International Council on Mining and Metals with all the big mining companies in it, a new scheme launched this year for mines that they can be accredited, or the control of finance from the Equator Principles, or something like aluminium stewardship that does go all along the supply chain and even has Marks and Spencers in it. So that's bringing us up to the front. And sorting out what are the things to go into these kind of schemes and how are they going to work, I think is an important area that geologists can contribute to. Now I can remember to give a name check to Nick Billam of very good Geological Society credentials, who's actually now doing a piece of research to work out how this kind of responsible sourcing for raw materials can work. So have a chat to Nick about that later. So if we want then responsible raw materials, then we have to know something about them. And I'm going to give you some examples now from my pet topic, if you like, the one I work on the most, which is the rare earth elements. And since I know that very few other people actually spend their days thinking about rare earth elements, although of course many igneous petrologists will be very familiar with them, here we are, 17 elements, scandium, yttrium, and the lanthanoids there. And they're in the newspapers again at the moment because China has some large deposits. They have had a very purposeful strategy of dominating the world market in mining rare earths and crucially in processing rare earths as well. And so on this map, you'll see all the big mines here in North and South China. And there are very few alternative supplies. Some small mines and a big one at Mount Weld in Australia is the main competitor really importing into Japan. And there was a big competitor here in Mountain Pass in America, but that went bust, and they're now putting their rare earths from near where Ed is onto a boat, and of course shipping them off to China. So China really has a very clever strategy here, and there is opportunity for more rare earth mines. If you want those magnets for cars and wind turbines, then there's certainly an opportunity to open more rare earth mines in the world. And the good news is there's loads of different deposits that we can look at. And so that's some of the research that we've been doing, is actually looking at some of those deposits. And it's not just to break the political stranglehold, if you like, but China has had a very poor environmental record, and it's trying to clean up its act. But this slide from Roskill, I think, is a real eye-opener. This portion in here with the exclamation marks is illegal supply from China. So this is something that can't be controlled to any Chinese environmental standards. This is being smuggled out inside cans of other material to go out to the world market. So we don't just want rare earths, we want responsibly supplied rare earths. And so there are two things that we've been doing as geologists. First of all, we need to understand the geology of these deposits to help companies explore and mine them. And so this is a slightly complicated graph, but it's just a schematic to show that we work on, from the bottom, igneous rocks, and you need some small partial melts from the mantle, you need some fractionation, and then you need some fluid processes. So that's what we would normally do as geologists when we look at rocks, and we've heard a fantastic talk by Marion already, interpreting the textures and how they form. But when I show you the next pictures, I want you also to think about this, because as an applied mineralogist, we also very much thinking about not only finding this material, but what happens when it's mined and processed. How will those minerals behave? And of course, that all now needs to be done in this cocoon of environmental and social responsibility. We don't want waste. We definitely don't want any toxic waste produced. And we need to get the most out of these things, use the least amount of energy and chemicals in our processing. So when I show you the slides then, you can think geology and paragenesis of the minerals if you like, but also have a think about the potential processing properties. How would you separate out your ore mineral from the other minerals in the rock? And I'm going to go to one of the project areas that we've been looking at in our SOS Rare project. So we're going to go exploring for rare earths in Malawi in East Africa on the East Africa Rift. And I'm actually going to pick one of the older projects that I did because it's one of my favourite places to talk about is the Camborne carbonatite in Malawi. There it is, stands up, it's a nice hill. You can walk up it, easy access, and go and collect rare earth carbonatite there. And in that carbonatite, I'm sure the colour's not bad here. So carbonatite is igneous rock made of carbonates. This is ferro and dolomite, the dark stuff. And here, can you see our rare earth areas in here? Green is monazite, and then it's got white strontianite in here. And these textures are pegmatite textures. And so that's something we've found. Although these are the weirdest magmas on Earth, if you like, they're carbonates instead of silicates. They actually behave in the final stages of their crystallization very like granites, which are some of the magmas with the highest amount of silica in them. And so you get a buildup of volatiles in there, undercooling, and then these beautiful, slightly smaller than in granites often, unidirectional crystallization textures. So they're pegmatoid textures. And that's some of the work we've been doing, is to understand this formation. And of course, if you're processing, finding a pegmatite kind of rock is fantastic. So this big brown blob here, this is one crystal from Wigu Hill in Tanzania. So he's that big, so you won't need very much mineral processing expertise to say that that is going to be jolly easy, is it not? However, with your microscope and an SEM, you look at this beautiful crystal from Wigu, which really excited the exploration geologists, and actually inside it looks very similar to this one. This is a Kangenkundi picture, but inside all of these beautiful unidirectional crystals here, whether it's at Wigu or Kangenkundi, in these transition environments there was just too much fluid there, and it's gone back through and altered them. And what we're seeing is not beautiful, big, easy to process crystals, but see in here a whole mixture of very pretty but small crystals in a pseudomorph. So we had the pegmatite, and then we had a pseudomorph texture afterwards. So they're all replaced with other minerals. And these, of course, can be jolly small, and at Wigu, actually, they're down to micron size. And instead of that beautiful big crystal being really easy to process, it's actually at the opposite end of processing world and is actually extremely hard to do by normal processing methods. And if I take this picture here, and we've got our monocyte crystals. Oh, sorry, that's just a gratuitous one to look at these long crystals and very beautiful textures inside these rocks. And again, these are mixtures and pseudomorphs after the original pegmatoid texture. And then let's go back into here again, and here's our monocyte crystals. And if I put this slide up here, then I should have 3 different sorts of monocyte. And here's one. This is Mount Weld, the big competitor to China, the mine in Australia, 0.5 millimeters. And these are small and very strongly intergrown with other phases. So this basically has to come out by flotation, which is slow, energy intensive, and quite expensive. And Kangenkundi is in the middle. And we think that could probably come out by some kind of physical processing. That hasn't been looked at yet properly, because actually Kangenkundi is under litigation, so that hasn't been going forward on a project. And it might get taken over by this one here, which is Eureka in Namibia. And here's the monocyte. And the monocyte crystals really are that big, and they're really not pseudomorphs. And so this one will come out by a very simple density separation. And that makes it enormously cheaper and less energy intensive and less chemical intensive than other projects, and therefore much more likely to go ahead, all other things being okay. And that's monazite, which I thought was a mineral that people might have heard about, the rare earth phosphate. But of course, when you come in to looking at these deposits that haven't been researched very much, you come across minerals that nobody's ever heard of. And so what we're having to do is to go and actually find out the magnetic properties and the surface properties of these minerals. It's called process mineralogy, to find out how they will behave in processing. And we've been doing that in SOS Rare, and then putting that together in a big European project with 12 partners on it to actually make new geomodels for alkaline rocks and carbonatites. And I'm not going to go through all these diagrams, but just to say that when we're making new geomodels now, it's not just about producing a lovely diagram like Mike Labar's here. We are interested not only in the geology, but in the processing properties, the environmental factors, the social factors, if we can fit them into our models, and also a mineral systems approach to learn from the oil industry about de-risking exploration. It's quite a big project. Hopefully we'll be in London to launch the results in November this year. And then coming back to SOS Rare, I want to jump to a slightly different way of looking at the geology then. So I said we want to get manufacturing right from the start. And this was a PhD project that we did in SOS Rare. Rob Powell did this work. And what we've done here is to do a life cycle assessment. So that's something very much used by manufacturing industry to look at the energy and other environmental factors. And you can do it right through a product lifetime. So you can do it for a whole car if you want to. And of course, people are doing this. If you want a low carbon technology or wind turbine or whatever, you want to know what the environmental cost of that is through the whole lifetime. But there aren't very many good LCAs on unusual raw materials like rare earths, for example, or lithium or any of these things. So it's a very new topic that people are working on. But what Rob's done here is not to go to an active mine and look at the LCA. We're looking at the pre-feasibility report that's produced by almost all companies as they go through the exploration and development process. And what he's been able to do is to take the data from somebody else's pre-feasibility report and model, and this is one of the LCA numbers, it's the kilograms of CO2 equivalent, so the greenhouse gas emissions, throughout the whole projected 45 years of the mine life of a proposed mine at Bear Lodge in the USA. And as it goes up and down, the ore is varying through what they know about it at the moment, and you can see the environmental footprint varying, so obviously higher grade is, in this case, is usually lower environmental footprint, as you might expect. And why is that important? Because at the moment there is no mine at Bear Lodge, there is no complete finished plan, and so at the moment, although the error is larger than if there were a mine, at this time everything can be changed. So it means when you're planning the mine, as you go into your feasibility study, not only can you plan for the economics of the mine going forward, but you can plan the environmental footprint as well to keep beneath a carbon footprint value or whatever it is that you want to do. So it means we can bring environmental planning into mining as well as economic planning. And so that's what's happening here. So at the moment, most people would go to a working mine and do a life cycle assessment. And we're saying go here through this probably 10 years as you open up a new mine and go to this pre-feasibility stage and do your LCA then, nice and early on when it's possible to make changes so that we can produce the lowest environmental footprint mine that it's possible to do. So I hope I've shown you that there is a role for geoscientists in manufacturing. By producing technology raw materials, we can help establish alternative supply chains to diversify and secure mineral supply. Hopefully we can help achieve that as responsible sourcing by finding deposit types that are good and establishing processing routes that are least expensive environmentally and also, of course, financially viable. And we really must, we think back to that diagram of the Ellen MacArthur Foundation at the beginning, make sure that we're linked through the value chain and that we can talk the same language as manufacturers so that we can really help get the manufacturing of all these technology that we need for decarbonisation exactly right from the start. Thank you very much.
Thank you very much, Francis. A very pertinent talk today, I think. Are there any questions from the floor? Yes, John Blundy there and one at the back.
Francis, one aspect of these high-tech metals is they often come from countries that aren't very prosperous. And the perennial problem of mining is that the countries that provide the raw materials rarely benefit. 50% of the world's cobalt comes from the DRC, which is probably in the top 5 poorest countries in the world. Is that something you think about in your projects? How can mining make sure that the countries, say Malawi, that provide these high-tech metals, actually have some material benefit from our usage of mobile phones?
So I would say that's absolutely embedded in everything we do, because you don't want to go into parachute into Malawi, come out again with your rare earths, and nothing else is left behind. And so right from the start, as soon as there's an exploration project, then it generates economic activity. And there's a huge amount of research that says what you should and shouldn't do in terms of interacting with the community. You don't just go and bribe them with pretty things that you give them anymore. You can actually do things. In Malawi, they've been building bridges so that they enhance the communications around, and things that the local people can maintain. Around that kind of social license, everything from governance to once the mine is working, you know that every mine that open will close. That's a fact once it's mined out and it's not economic. And there are ways now you can push other businesses and things to start up as the mine is running. We have a fantastic example in Namibia where we took one of our high-tech alcarb project workshops out there to see what they're doing and learn best practice. Yep, so we're absolutely trying to combine that and push it out. I have a PhD student in Indonesia who's advising the regional governments there on starting bauxite mines and things. So we try and cross-fertilise between all of these things. It's essential. Yeah. And you want to look up World Bank Climate Smart Mining. It's really easy to Google. Got a fantastic infographic. And they've picked up on this fact that indeed we need these raw materials. And there are many developing countries that would like to benefit from them. And they're starting a whole initiative on making sure that the mining is a benefit to them and not the proverbial resource curse. Yeah.
That's very reassuring. Thanks.
And question at the back.
Francis, that was very interesting. Thank you very much. My name is Camborne Davis, by the way, ex-Applied Geochemistry Research Group at Imperial. That's very interesting, but looking at your original map, it's heavily skewed towards China. Is that because us geochemists and mineral exploration companies in general have kept well away from rare earths, and the Chinese have got there first? Have we clocked on too late, or not too late, but could we push that map into other sources worldwide? Because there's a huge variation in geology worldwide, and it seems very, very strange, just on a simple, straightforward basis, that it should be skewed towards China, which has varied geology, but so is elsewhere.
Right, I think you're trying to think of a short answer. So the short answer to that question is that is a political map, and if I'd had a slightly longer, I took it out, I could have shown you another diagram with a huge number of coloured spots of rare earth deposits all over the world. Now, China happens to have the Bayanobo deposit, which is the biggest deposit in the world, so they were fortuitous in having that. They realised they had it. There's a plaque there saying, as Saudi Arabia has oil, China has rare earths. And so they mined the rare earths from Bayanobo. They found some other deposits, very interesting ones in South China, and they kept the price low, and they pushed everybody else, including poor old Mountain Pass in the USA, basically out of business. They did it on purpose, and it was extremely clever, and they're reaping the rewards now. But geologically, there's many other rare earth deposits we can use.
Okay, thank you very much. Well, okay, Andrea, yes, very quick. As you're a medal winner, you get.
I'll do a quick answer.
Yet to find the rare earth elements, and how does it project with respect to the increasing demand over the next decades? What's the estimate?
Okay. Oh, oh dear, there is no short answer to that. Let me talk. The estimates for neodymium need to go up. That's the important point. But as we stop using petrol cars and things, the estimates for the use of some of the other rare earths may actually go down. And so for rare earths, it's quite a complicated balance problem. But we did, I'm trying to remember exactly what the figure is. We did a calculation, Richard Harrington, a colleague of mine, sat down with his calculator and worked out what we'd need to do the climate change committee's projection for electric vehicles in the UK by 2035. And I think you need all of the neodymium production from the world just coming into UK over the next few years in order to manufacture that. So it's a lot.
Thank you.
Well, as they would say on Top Gear, on that bombshell, I think we'll say thank you very much, Francis.